So let's continue our tutorials on the carbonyl condensation reactions. In the previous video, we looked at an aldol condensation reaction where we said if we have an aldehyde or ketone subjected to a basically a weak base, we are going to have a formed carbanion which will undergo a reverse reaction with the remains of the carbonyl compound if we use a weak base. So let's extend the carbonyl compound from aldehydes and ketones to esters. So what if we have this compound? This is an ester in the presence of a weak base. What will happen? So in the previous video we said that this carbon is an alpha carbon and has alpha hydrogen on it. So you have this compound, or this compound in a basic solution, and this one is a weak base. This hydrogen here is acidic because of the induction by the oxygen. So this base can abstract the hydrogen on the alpha carbon. For that matter, we are going to have a formed negative charge on the alpha carbon shown here. So which is going to be like this. So we are going to have the ester formed with a negative charge on the alpha carbon. Now, because of stability, this compound can undergo resonance to ensure stability, where the electrons here can be pushed towards the carbonyl carbon, then the pi electrons will move towards the oxygen. So we are going to have a resonance stabilization, where this carbanion will resonate to form what we call an enolate, which looks like that. So these compounds are resonance structures. So if we use a weak base, what is going to happen? Now you're going to have a partial deprotonation of the starting material. So the formed carbanion can react back with the remains of the starting material, basically as the carbonyl carbon, because that is where it has a partial positive charge. So this carbanion can reversibly bind with the carbonyl carbon of the starting material. When that happens, there's going to be a bond breaking, which will look like this. So how will a joining look like? So let's see how we can join these two compounds together. So if you join this compound to this, we are going to have this intermediate being formed. Let's draw the side of the compound first. So we are going to have this side. So this compound is the carbanion that will bond to the starting material, which will be like this. So it has the oxygen, which will be a negative charge because the pi bond has broken. Then it will have an extending methoxy group, which is this one. Then this one, the remains will continue like that. So this is the joining. So basically this is where the intermediate is formed. Now because of stability, for stability to be formed, the lone pairs on this oxygen will form back. So the lone pairs on this oxygen will form back to the position. So we assume the carbonyl carbon or the carbonyl bond again. Then the methoxy group will now leave the system. So when it leaves, we are going to have the product which will look like this. So we're going to have a newly formed ketone at the position. Then this methoxy has left the solution. So we are going to have the ethyl group. So we have this one plus the methoxy group that left in the solution. This product is a Claisen product. So we have two esters, or let's say we have one ester in a weak base. There is going to be a partial deprotonation. Then the remains will react back with the carbanion, so we formed a beta keto ester. So this is an ester. A Claisen product is basically an ester that bears a ketone group at the beta position. While we said an aldol product is a carbonyl system with a hydroxy group at the beta. So take note, this is the functional group of a Claisen product. So if you get it wrong, You can just access yourself from here. When you formed any Claisen product, you must be able to see this functional group in it. So you have an ester, and the beta position of that ester has a ketone. Let's try a different example and see. What if you have this? So let's say you have this ester. In a basic solution, what will happen? So in some cases, you can be asked that this one is having 2 moles. So if you use a strong base, you have to use 2 moles of the starting material. If you use just a weak base, you are going to use just 1 mole, where we are going to have partial deprotonation. Then the remaining can react back to the starting material. So when you have this one, of course, this carbon has a hydrogen, which is silent. So the base can abstract this hydrogen. Then we form our original structures, where we have first the carbanion, which will look like that. So we have the carbanion with the negative charge here. Then it will undergo resonance to form the corresponding enolate ion. So when you form the enolate ion, as we said earlier, the carbanion here will come back to react with the remain of the starting material. So when that happens, it's going to be what we call a flip-flop mechanism, where this bond will move up and the pi bond or the pi electrons will shift in again. So in some books you can see a flip-flop arrow, where one side moves up, one side comes down, or you can have an arrow which goes up with both head like this, means it goes up and down. So we have a flip-flop mechanism. Then the ethoxy group here will leave. So when it leaves, what are you going to have? We have this one joining this. So we are going to have this product which will look like this. So we have first our methoxy group, linked to a ketone. So the ketone is linked to this carbon. So it has this one. This, okay, let me erase this arrow so it can clear. So this drawn compound is the carbanion. Then the carbanion can now link up with the ketone of the starting material, which will be like this. Then you add the remain of the starting material. So this is the product that is going to be formed when you have this compound reacting itself in a basic solution. So the trick here is, for every Claisen product, the 2 ketones must have just 1 alpha carbon between them. So this is the functional group of a Claisen product: 2 ketones with just 1 alpha carbon between them. When you solve and you get 2, then it means you are going to have it wrong. Let's solve the last question. So I want you to pause the video and try your hands on this question. What do you have this? So what if you have this compound? You have this compound plus this compound, the 2 in a basic solution. Go ahead and predict the product which will be formed when this compound and this compound reacts in a basic solution. So you are going to have first the carbanion formed here, because this one has alpha carbon with no hydrogen. So the carbanion formed here will come back and react with the ketone group of this one. Despite this one, if there's a strong base, you are going to have this mechanism where this one will come and react with this. So when this one reacts with the carbonyl carbon of the first compound, the product is going to be like this, as we said, for all the carbonyl that receives the attack, that is where there is loss of the alkoxy group. So this one will leave the system, so we can get this product. So we get this benzene ring bonded to the ketone. Then because the methoxy has left, that bond will be given to the alpha carbon of the carbon ion. Then we can now get what? The product. So let's apply this knowledge once again and predict the product for this reaction. So we're going to use the same starting material. So let's say you have this starting material plus acetone what is going to be the product for this reaction in a basic solution. So here the idea here is always the formed carbon ion will go and attack the remains of the starting material or the electrophile. So here it is a ketone and an ester. So a Claisen cannot only be two esters, bear in mind. We can have a ketone and an ester. In such case, you are going to have the carbon ion formed on the alpha carbon of this. This one has this as alpha carbon, but it has no hydrogen. So in that case, this alpha carbon or this carbon ion will come and attack the carbonyl or the starting material, the first compound. So when this one leaves the system, this bond is going to be given to the alpha carbon of the acetone. So the product will now look like this. Okay, so we have this one as the benzene, this as the benzene. Then this bond will be given to the alpha carbon of the acetone, which will look like this. So in that case, we're going to have two ketones in the product. So in cases where you use a ketone or even an aldehyde and an ester, you are going to have two ketones flanked by this. So either this one or that one is a Claisen product. So for us, the two ketones are separated by one alpha carbon between them. This type of reactions are what they call Claisen condensation reaction. It is a Claisen reaction. Now let's look at different forms of the same person or the same mechanism. So let's say you have this. Let's say we have a compound. This compound. So here you have two esters in the same compound. So far for what we have done, we have one ester in that compound. So we have two esters in the same compound. What will happen? Now here the idea here is if we have two esters, in this case we can have two centers for carbon ion formation or alpha proton abstraction. This is an alpha carbon, this is an alpha carbon. So if you have this one in a basic solution, the compound can choose to form a carbon ion at the center or a carbon ion at the center. Now because of stability of a ring nature, if you form a carbon ion at the center, the negative charge here will come and attack the farthest carbonyl compound or carbonyl carbon in the same molecule. If you form the negative charge at this carbon 2, this one will come and attack the same or the farthest carbonyl carbon in the same molecule. You're going to have it as 1 and 2, just like how we did in the previous video on the intramolecular aldol condensation reaction. For this one, we have two esters in the same compound. For the intramolecular aldol condensation, you have two ketones or two aldehydes in the same compound, or an aldehyde and a ketone in the same compound. When we have two esters in the same compound, of course, it will undergo a same reaction as a cleansing reaction, where one ester will react with the farthest carbanion. This type of reaction, where we have two esters in the same compound undergoing an intramolecular cleansing condensation reaction, is what we call a Diekman's reaction. So the Diekman's reaction, as we wrote earlier, the Diekman's reaction is an intramolecular cleansing condensation reaction. This reaction occurs when we have two esters in the same compound, and for that matter, there's going to be an intramolecular reaction where we can convert the starting material to the cyclic structure. So let's see how we're going to draw the structure of the product for this. Okay, so let's look at something. Let's join this side or this side, this carbanion to this carbanion. So look at this. This compound is symmetrical, meaning when you form the carbanion here or you form it here, the two products either here or here are going to be the same. But if they are not symmetrical, then we are going to have two different products for that. So let's try for the symmetrical one, then we do another one for the asymmetrical one. So for this, whether you join this side to this side or you join this side to this side, it is still going to be the same because it is a symmetrical compound. Let's look at this. If you want to join this side to this side, now the carbons in the ring will form, or the carbons in between the two, or the terminal carbons will form a cyclic structure. So starting from here, 1, 2, 3, 4, 5, 6. These 6 carbons will form what? A cyclic structure. And the ones which are not inside that structure will be called a substituent. So let's draw your hypothetical 6-membered ring, which will look like this. We are going to have this 1, 2, 3, 4, 5. So here is what? 6. So if I'm joining this carbon to this carbon, then I can see this carbon is this. So if this carbon, this alpha carbon is this one, then of course I'm going to extend with an ester, which will look like that. Next, if this carbon is this, then this one too will have what? An ester, which will look like that. So this is just a hypothetical 6-membered ring structure. So what is going to happen? The carbanion formed here can now come and attack this carbon. When it attacks this carbon or this methoxy group, will leave away from the system. So our product is going to be like this. We're going to have this product, which will look like that. So we have our 6-membered ring, which will look like this. Then this side will possess a ketone with an extending methoxy. Then this side also possess a ketone. An intramolecular cleansing condensation reaction, where we have two ketones, this one and this one, flanked by or separated by 2 alpha carbons between them. This product is what we call a Diekman's product. A Diekman's product. Okay, so let's try another question, which I would like you to pause the video and try, then compare your answer. So let's assume we have this structure. Let me change the color so that you have, let me use okay, let me use this one. Let's use this one. So we are going to have this compound. This is an ester. We have this one, then with another N, which is a methyl. Let's assume we have a methyl here, then we have an ethyl here. Now this compound, when you have a basic solution, can form two Diekman's products, 1 and what, 2. So draw the structures of the two products which will be formed from this if you have this one in a basic solution. So pause the video and draw your structures and let's see. Okay, so let's do it together. So with this one, you can form carbon ions at two centers, either here or here. So when you form the carbon ion at this point, it will come and bond the farthest carbonyl carbon, which is this. So let's say here is structure 1. When you form the carbon ion at this center, it will come and bond the farthest carbonyl, let me change the color of this one so maybe it can be clear, make it red. So when you form here, this one will come and bond the farthest carbonyl carbon, which is this one. So we can have the blue structure or the red structure. So let's see how they all look like. Let's first draw the red structure and see. So when this carbon bonds this, you're going to have how many carbons in the ring? We'll have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 carbons in a ring. So for the red one, this is how it's going to be. You're going to have an 8-membered ring, which will look like this. So like that. So we have this one, have this one, have this one, have this one, have this. So this is our 8-membered ring. When this one bonds here, so you are going to indicate any two adjacent carbons as this and that. So let's say this center is our this carbon, therefore this center will become this carbon. So let's see how we are going to draw the product or let the substituent on them. So if this carbon here is this, then of course it's going to have an extending ester, which will look like that. Then if this carbon is this, then after this one bonding this, the ethoxy group here will leave away from the system. So we're going to have just a ketone on this carbon. Now if this carbon is this carbon, then 1, 2, 3 away should have a methyl. So 1, 2, 3 should have a methyl. Now we said this carbon is now this. So the next carbon, which is this, also has an ethyl group. So this is the structure for the red one. Let's propose the blue one. I hope you tried it. So did you get it correct? Drop your response at the comment section. Let's take the blue one, where this side will bond to this side. So that one you have 1, 2, 3, 4, 5, 6, 7, 8. Also 8-membered ring. So let's draw our 8-membered ring, which will look like this. So we have this one, that, 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 that. So this is our 8-membered ring. Now if this carbon bonds to this, label any two adjacent carbons in the ring as this one and that one. So to me, let me see, I want to label this carbon as this. So I'm going to label here as this one. So if this one is this, then the extension, we are not part of the ring, is what? An ester which will look like that, with an extending ethoxy group. If this carbon is this, the next carbon, which is one, becomes the adjacent carbon here. So when this one bonds, the methoxy group will leave away from the system. So we are going to have a ketone on this carbon like that. So we have this. So let's continue. We said this carbon is this. So the next carbon away from that has a methyl group. Now we said this carbon is this. So the next two carbon, which is 1, 2. Sorry, I think it's 1, 2. So it's 1. I think I did a mistake somewhere here. Let me delete it. So this carbon is this. So it is 1, 2. So it is this 1, 1, 2. The methyl group will come here. Then if this carbon is this, then the next two carbon, which is 1, 2, will also have what? An ethyl group. So 1, 1, 2 will have an ethyl group. So this is how the structures will look like. This is the blue one for this. Then this is the red one. For this. So these are the two products. So basically, when you have two esters in the same compound, there's going to be an intramolecular Claisen condensation reaction. And after that, you are going to form a cyclic beta keto ester, which we call what? A Diekman's product. So Diekman's product is basically an intramolecular Claisen condensation reaction. So try your hands on these questions and send your answer to the email or the WhatsApp at the description section. So take this once and try your hands on. So let's say we have this. So this one, with your knowledge in an intramolecular aldol condensation reaction, which is the video on the channel, then with the knowledge with the Diekman's reaction, propose the two products for this reaction. So with this, one is going to be an intramolecular aldol condensation product, and one is going to be a Diekman's product. Read the answer and drop your response at the comment section or to the email or the number at the description section. The next, try this one and let's see. So we have, let's see, have this one. With hydrogen. Then let's say I have here a phenyl group bonded, and here I have a methyl group. So try your hands on these two and send your answer to the identities at the description section. Thanks for watching. Don't forget to subscribe to watching so you can receive every bit of update from this channel. In the next video, we're going to look at the Michaels addition reaction and Robinson annihilation reaction. Subscribe and stay tuned. Thank you.